Many of the random finite sets that we consider in this course are defined as the union of independent random finite sets. For instance, the set of measurements is described as the union of the clutter measurements and the object measurements. Given the distribution of the independent random finite sets, we need to be able to describe the distribution of their union. We normally do this using something called the convolution formula. And this formula is therefore used over and over again in the rest of this course. Before presenting the convolution formula for random finite sets, I'd like to present the convolution formula for discrete random variables, since that is closely related and perhaps something that you can relate to more easily. The objective in this part is to describe the probability mass function for a random variable which is the sum of two other random variables. Suppose we toss a coin 2 times, and that x is the total number of heads. If x1 is the number of heads in the first toss, and x2 is the number of heads in the second toss, it follows that x is x1 plus x2. We assume that x1 and x2 are independent. In both tosses, we assume that the coin is fair, and that the probability to obtain 1 head is 0.5, and that the probability to obtain 0 heads is 0.5. Now, how can we use the distributions of x1 and x2 to find the distribution of x? Let us start with the probability to obtain 0 heads in total. Since this can only happen if we obtain 0 heads in both tosses, the probability that x is equal to 0 is the probability that x1 is 0 times the probability that x2 is 0, which is 0.5 times 0.5, which is 0.25. Similarly, the probability to obtain 2 heads is the probability to obtain 1 head in the first toss times the probability to obtain 1 head in the second toss, which is also 0.25. More interestingly, to obtain 1 head in total, we can either have x1 equal 0 and x2 equal 1, or x1 equal 1 and x2 equal 0. The probability that x is 1 is therefore the sum of the probability that x1 is 0 and x2 is 1, plus the probability that x1 is 1 and x2 is 0. The probability that x is 1 is therefore 0.5. Let us look at a second example, where we are instead rolling a die 2 times. Similarly to the previous example, x1 is the number of dots in the first roll, x2 is the number of dots in the second roll, and x is the total number of dots in the 2 rolls. Suppose we want to compute the probability that we obtain 4 dots in total. There are 3 ways to obtain 4 dots. You can obtain 3 dots in the first and 1 dot in the second roll. You can obtain 2 dots in both the first and the second roll. Finally, you can obtain 1 dot in the first and 3 dots in the second roll. The probability to obtain 4 dots is therefore the sum of the probabilities of these 3 events. Since the probability of each event is 1 divided by 36, the total probability is 3 divided by 36, or 1/12. Having looked at 2 examples, we are hopefully ready to understand the general case. As before, we assume that x1 and x2 are independent and integer-valued random variables, but they can now have general probability mass functions. As long as x1 takes some value s and x2 takes the value v minus s, the sum will be v, regardless of the value of s. Of course, for many values of s, the probability that x1 is s times the probability that x2 is v minus s might be 0. But by including all terms, we obtain an expression that holds for general PMFs, px1 and px2. I encourage you to compare this to the 2 examples above and verify that the results hold. Now, if you remember the definition of a discrete convolution, you can see that this summation is the convolution of px1 and px2, evaluated at v. The intuition that we had for discrete random variables can help us make sense of the corresponding relations for random finite sets. Suppose x1 and x2 are 2 independent random finite sets. Now, we cannot add sets, and instead we are interested in forming a set X, which is the union of x1 and x2. To get started, let us check how we can evaluate the multi-object PDF of X for a set with a single element 1.3. In order for X to be this set, either x1 is empty and x2 is a singleton set with the element 1.3, or x1 is a set that contains the element 1.3 and x2 is empty. To compute the multi-object PDF of X, we need to consider both of these possibilities. Now, there is one tricky aspect to this, and that is why there is not a third term for the possibility that both x1 and x2 contain the element 1.3. In theory, this would also yield the same set X. A first remark is that it is generally physically impossible to have two objects at the same location, and it's therefore not a problem that we don't have a term corresponding to this event. One way to reason about this intuitively is to consider the probabilities that these multi-object PDFs are related to. The multi-object PDF on the left-hand side is related to the probability that the set X contains a number x tilde in a small interval around 1.3, say between 1.2 and 1.4. The right-hand side is instead related to the probability that x1 is empty and x2 contains the number x tilde, plus the probability that x2 is empty, whereas x1 contains the element x tilde. If you look closely at this expression, you can hopefully agree that the relation between these probabilities makes sense. So what about this third term that we have excluded? Well, if we were to include a third term, where both x1 and x2 are the same and contain the element 1.3, I would argue that that term should be related to the probability of the event that both sets are equal to a set that contains an element x tilde, where x tilde is in the interval between 1.2 and 1.4. However, the probability that both sets contain the same element x tilde is 0, under the assumption that elements in the sets are continuous valued random variables, and the corresponding density can therefore be ignored, since it must be 0. Admittedly, this argument is vague, and I understand if you find it difficult to grasp. A better argument for the above result is that there are solid mathematical proofs of these relations, but unfortunately it is beyond our scope to include them here. Let us return to the example where X is the union of the independent sets x1 and x2 and study how we can evaluate the multi-object PDF of X for the set 1.3, 2.7. When the set contains two elements, there are four possible explanations. There are two ways that one of the sets could be empty, either that x1 is empty and that x2 contains both 1.3 and 2.7. Or that x2 is empty and that x1 contains both 1.3 and 2.7. There are also two ways that the sets x1 and x2 can contain one element each. Either x1 contains the element 1.3 and x2 contains the element 2.7, or the other way around. As you may guess, this becomes increasingly complicated if we want to evaluate the multi-object PDF of X for sets with more elements. However, there is a nice, elegant, and general way to express the multi-object PDF of X for any set X, namely as a sum over all subsets x1 of the set X of px1 of x1 times px2 evaluated for all elements in X that are not in x1. If you want to use this formula for the above example, where the set X contains the elements 1.3 and 2.7, there are four different subsets of X, namely the empty set, the set that contains both 1.3 and 2.7, the set that only contains 1.3, and the set that only contains the element 2.7. It is easy to verify that the equation given in the above example precisely matches the general formula given below. If you look at the general formula, you may also notice a certain resemblance to convolutions. In many cases, we take the union of several random finite sets, and it's therefore important to generalize the above formula. To do this, we introduce a symbol that denotes the summation over all mutually disjoint sets, x1 to xn, whose union is the set X. This may look a bit complicated at first. Please recall that sets are disjoint if their intersection is empty, and mutually disjoint means that none of the sets share any elements. A convenient way to understand this notation is to look at a few examples. As a first example, consider the summation over all disjoint sets x1 and x2, whose union is a set that contains the element 1. In this case, there are two possibilities. Either x1 contains the element 1 and x2 is empty, or x1 is empty and x2 contains the element 1. In both cases, the intersection of the sets is empty, whereas the union of the two sets is the set with the element 1. If we instead have a summation over mutually disjoint sets x1, x2, and x3, whose summation is a set with the element 4, there are three possibilities. In all three cases, two of the sets are empty, whereas the third set contains the element 4. In all cases, you can see that the intersection between any pair of sets is always empty, whereas the union of the three sets is the set with the element 4. Naturally, the sets may also contain more than one element, and if we look at the summation over disjoint sets x1 and x2, whose union is a set that contains the elements 3 and 5, there are now 4 possibilities. You can again verify that the intersections and unions of the two sets are correct in all 4 cases. You may have noticed that the expressions in the first and the third example resemble the expressions when we had unions of two sets. In fact, for unions of two random finite sets, we have simply invented a new way to express the same summation. It is possible to view it as if we are assigning elements in X to the sets x1 to xn. Every term in the summation can then be thought of as an association hypothesis. This is particularly useful when we later use the convolution formula to express the measurement model. We are now ready to present the general formula. Suppose x1 to xn are independent random finite sets. If X is the union of x1 to xn, the multi-object PDF of X, evaluated for a set X, can be written as a sum over all mutually disjoint sets x1 to xn, whose union is X, of the product over the multi-object PDFs of x1 to xn. This essentially means that we obtain one term for every possible way that we may have generated the set X. For instance, suppose X is the union of 3 independent random finite sets, x1, x2, and x3, and that we want to evaluate the multi-object PDF of X for a set that contains the element 4. Then there are 3 possibilities. In all 3 cases, one of the 3 sets contain the element 4, whereas the other 2 sets are empty. In each term, we have a product of the multi-objects PDFs of the different sets, which makes sense since the sets are independent. Let us finish with yet another example. In the previous video, we considered a problem where the random finite set contained 2 independent variables, x1 and x2, and we gave an expression for the multi-object PDF of that random finite set. We can use the convolution formula to verify that the expression that we provided was correct. To connect that example to the convolution, we need to realize that a set that always contains the elements x1 and x2 can be described as the union of 2 singletons, one that contains the element x1 and another that contains the element x2. If you find this difficult to understand, you can ignore the connection to example 2 and view the results on this slide in isolation as another example of the convolution formula. So, let's assume that x1 and x2 are independent random finite sets that always contain precisely one element each, such that their multi-object PDFs are 0 if the set does not contain precisely one element, and pi of xi if the set contains the vector or number xi. Now, if the random finite set X is the union of x1 and x2, we can use the convolution formula to describe its distribution. For instance, to evaluate it for the set x1, x2, we get a sum with 4 terms, since there are 4 ways to express this set as the union of 2 disjoint sets. In the first 2 cases, one set is empty, whereas the other set contains both elements. Considering that the sets x1 and x2 always contain precisely one element each, both of these terms are 0. In the last 2 terms, the sets x1 and x2 contain one element each. Either the set x1 contains the element x1, and the set x2 contains the element x2, or the other way around. By plugging in the expressions for the multi-object PDFs of x1 and x2, this simplifies to p1 of x1 times p2 of x2, plus p1 of x2 times p2 of x1, which was the expression that we used in the video about multi-object PDFs.